So, as you just said, I'm going to talk about the possible effects of Lorentz invariance violation in the neutrino flux. So, we start as always trying to unify quantum mechanics and general relativity. And this leads us to change our concept of space-time. And one natural way to do that is to consider the violation of the fundamental symmetry of space-time. This hypothetical violation of the space-time is supposed to be small at the usual energies, but becomes important at higher energies and also be accumulative. So the effect increase with long distance. This makes the observation of high energy exoparticles one of the best ways to look for this Lorentz invariance violation. In particular, we can focus on the neutrinos because they travel mostly free because they have very few interactions. They also can contain already signs of new physics, like, for example, their masses. And of course, because in the last decades, we have access to observations of high energy neutrinos thanks to the new observatories like, for example, IceCube, who are the ones who discovered the first PeV neutrino. Many theoretical frameworks lead to modify dispersion relation of this kind, which depends of two parameters, the order of correction, and also the leaf parameter that is usually written as the inverse of some energy scale that is usually related with the Planck mass. So focusing on the superluminal case, we get that the neutrino becomes an unstable particle that can disintegrate through vacuum power emission and the neutrino splitting. The vacuum power emission consists of the production of electron and positron, and as these particles have mass, these require a minimum of energy, so this process has a threshold, which depends on the scales of new physics. On the other hand, the neutrino splitting is one neutrino transforming in three neutrinos. If we approximate that the mass of the neutrino is almost zero, this has no threshold. So now, we want to construct a very simple model, a toy model for this. If we consider a neutrino traveling free from the emission to the detection, the neutrino will lose energy due to the expansion of the universe. This is perfectly defined. But in the moment the energy has enough, the neutrino has enough energy to produce the pair emission. The pair emission is a probabilistic process in which the final energy has a probability distribution. So now the energy at each point of the trajectory is not defined anymore. It's a probabilistic effect. We can still define, for example, the mean energy loss in the process using the probability distribution. But we don't have a defined energy. So one possible way to make a very simple model is to identify the energy of the neutrino with the mean energy. So the previous equation became some kind of evolution of the energy in the process of vacuum pair emission. If we solve the equation and add the effect to the expansion, we have this equation for the evolution in the case of only BPE and expansion. The contribution of the BPE can be written, as you can see, in terms of a scale of energy that emerge naturally from the combination of all the constant that appears in the decay width. If we integrate the previous equation between 2 points, we see that the classical relation transforms is modified to this new relation. And we have two different, but very differentiated regimes. If the energy is above this new scale of energy, we see that thanks to the exponent, the strong exponent in the quotient, the change in the energy will be very, very strong. And otherwise, if the energy is below this threshold, this scale of energy, the effect is almost negligible, and we can recover the previous relation, the classical relation. So we see that this scale of energy acts as an effective threshold. But we should remember that we also have the real threshold. So which one of the two thresholds is the one we can observe? But is the larger one? But which one of these two is the largest one? These two scales of energy depends of the scale lambda, the scale of new physics. So this is actually a function of lambda. And if we plot this quotient as a function of lambda, we get that the biggest one is the real threshold, and the other one is of energy below the real threshold, the effective threshold. This relation, this hierarchy, can change for very big values of lambda, but these values of lambda are above the Planck scale. So for all our interest or range of interest of possible values of the scale of new physics, the real threshold is always above the effective threshold. It's also worth to notice that if we have the process of BPE, that means that we are above the real threshold, and that means that necessarily we are above the effective threshold. So we are always in the strong regime. So the effect is always very strong and very fast. Now, in the classical case, if we want to know the flux of neutrinos for some detected energy, once the detected energy is fixed, we can find always the necessary emission energy, the only one compatible with each source location from the classical equation of the redshift. And then we can just integrate the flux from one source to all the possible location of the sources. The thing is that if we try to do this with including the effects of the BPE, what we get is that if we plot, for example, the emission energy as a function of the location of the source, we get that for a certain source, this relation has a singularity. It goes to infinity. That means that there is a source which has to emit a neutrino with infinite energy in order to be detected with energy ED. This puts a limit in the compatible sources. We cannot have a source above this critical source, because it would require an energy more than infinity, an energy more than the maximum energy we are considering in order to be detected with energy ED. This implies that the previous equation of the flux that at first goes in all the range of possible sources, now the integral is only up to this critical source. Okay, but what happens if this critical source, this critical source is a function of the detected energy. If we increase the detected energy, the critical source is smaller and smaller. What's happened to that energy in which the critical source has the value of the minimums, the first source we are considering in our model? In that case, the integral has zero domain of integration, so this integral is zero. So we have zero flux of detected neutrinos. So we see that we can say we have a cutoff in the neutrino spectrum for that value of the detected energy. But that value of the detection energy maybe is some kind of difficult to solve from this equation. So we can make an approximation, and the approximation says that the energy in which we can find a cutoff is the scale of energy, the dominant threshold in the process, divided by 1 plus the closest source. Okay, it's worth to notice that the existence of the cutoff at its location doesn't depend of the shape of the distribution of sources. It only depends of the dominant threshold and the position of the first source. Okay. Now, this is only a model for expansion per production, but now we want to add the neutrino splitting also. Well, as the effect of the production, the per production, is very strong and fast, we can think an approximation, an instantaneous approximation in which we substitute the emitted neutrinos directly in the source by the number of neutrinos in the ends of the cascade of this integration shower. This can be done also for the neutrino splitting, because the neutrino splitting has formally the same dependence in the energy than the pair production, and also can be written in terms of an energy scale. So we can substitute the number of emitted neutrinos who are above the threshold, this effective threshold, by the number of the neutrinos at the end of the shower of disintegration. That is 3 to the power of the number of disintegrations of the emitted neutrinos, which now have the energy which is exactly the threshold, and they will only suffer expansion because they have not enough energy to produce the effects of new physics anymore. Using this description, we can describe both the pair production and the neutrino splitting, and we can add the effects. So adding the effects and adding also the expansion of the universe, we can analyze the new flux, and we see that the new dominant energy scale is this new effective threshold from the neutrino splitting. You can see this thinking in the example of even if the neutrino has reached the expansion, the pair production threshold, if has enough energy to produce neutrino splitting, he will continue losing energy until he reach the effective threshold of the neutrino splitting. So now, as the dominant energy scale that governs the cutoff of the process is the effective threshold of the neutrino splitting, now the new location of the cutoff is the energy scale of the neutrino splitting divided by 1 plus the closest source. This is the new position of the cutoff. Okay? So now, this is like a summary of what we have learned only using this toy model. In the first place, a superluminal modified dispersion relation seems to lead to a cutoff in the neutrino spectrum, and this is independent of the source distribution. The position of this cutoff, it only depends of the dominant energy scale, the dominant threshold, and the position and the location of the closest source. Secondly, we can write the location of the cutoff as a function of the new physics energy scale through the definition of the threshold, which depends of the scale of new physics. Then the energy scale that governs the cutoff can be either a real or an effective threshold. I mean, the dominant threshold can change, we have seen, as a function of the scale of new physics. But fortunately, for all the scales of new physics below the Planck scale, which are the interesting ones, the relation doesn't change. The hierarchy of the energy scales are always the same. Okay, so now we can see some applications of this toy model, very simple applications. In fact, for example, ice cube detector have recently observed the neutrino of the glacial resonance we have mentioned before of 6.3 PeV. So if there exists a threshold, it has to be at energies greater than this 6.3 PeV. So putting this condition in the definition, the equation of the cutoff as a function of lambda, we can get a constraint in the possible values of lambda. And for examples, for 6.3 PeV, we get that lambda has to be greater than this quantity, 0.003, the Planck scale, the energy of Planck. But we can use this relation also in the other way around. We can ask where it should be the cutoff location for certain value of the new physics energy scale. In fact, we are interested on a new physics energy scale near to the order of the Planck scale. So if we put this in our equation for the cutoff, we get that this is around 100 PeV. 100 PeV is not that far as we could think at first. For example, the future detectors like IceCube Gen 2, which aims to be sensible to up to the exa electron volt, would be already prepared to detect a cutoff if the cutoff is in 100 PeV. So this last slide is like a motivational speech saying that there are some models that predicts signatures of new physics that can be detected already by the next generations of detectors. That's all. I think I've gone too fast.
That's very right. Questions, especially from fellow students? I start asking one question, maybe while waiting. Going back to your last slide, yes. So here you have, I didn't understand, you have the 3 parameter n and the minimum redshift. So what did you use there?
I have used.
You work out the definite number. So what?
Yes, I have put in the minimum in the cluster source the most restrictive one for this value, which is the limit going to 0. So the cluster source as near as it can be.
So that equals 0.
Yes, and the other thing is the order of the correction. In this case, if order 2, the n equal 2, because if you put n equal 1, you get a value of the location of the cutoff that is already it's not possible because it's also, we have
a lower cutoff.
Yes, it's a lower cutoff.
So you could say that you're already excluding n equal 1.
Yeah. Yeah. Sorry.
So the neutrinos should come. So if I understood well, I don't know if I understood what you did, but then the neutrinos should be produced in the propagation, so that you depend on the astrophysical scenario that you have at the sources, right? So
yes.
Depending on the flux that of the protons or the nuclei that come out from the source. So then I understand that this you didn't consider yet, but so you didn't, right?
Yeah, I mean, let's write an equation from the sources here.
Okay, so that should be inside that L that you.
Okay, the production in the source. Okay, we simply follow the power law. Power law with with an 2 exponent 2, but we have not tried other kind of luminosity relations.
And then I think I didn't understand why you say that it doesn't depend on the distribution of the sources, because that should enter in this row of Z.
Yes, if you want to draw the flux, because you want to know the shape of the flux in order to compare with the data, obviously you need the distribution of sources, and the flux will be highly dependent on which distribution of sources you use. But as the distribution of sources is still not clear, I try to get some information that doesn't depend on the distribution of sources. And that's, for example, the comparison of the limit of integrations, the minimum position and the maximum position of the sources. And what they said is that with the new physics, there exists a critical source that will suppress this integral, and this is independent of the distribution of sources. It only depends on the first source.
Okay. No, I just wanted to say that depending on the composition of the cosmic rays and on the maximum energy and on the cosmological evolution, you might have a very big difference between the expectations of the neutrino fluxes. So probably this will be important for your.
Yeah, this is highly depending on the distribution, but I was.
No, not only on that, because if the cutoff of the neutrino flux is also dependent on the maximum energy of the protons. So it's not just depending on the.
Yeah, but that for the. You are talking about the neutrinos, the cosmic generated neutrinos,
yeah.
But this can be also neutrinos from point sources.
Okay, directly from the sources. Okay, yeah, I see. Thanks.
Okay, thank you very much. I think we need to go to the next speaker. So thank you very much, Maykoll. Next. Please. Oh, okay, I can say it. Jelena Strišković.
Yeah, good enough.
I'm sorry. And she's going to illuminate us about likelihood or unbinned. Thank you. I will warn you 10, 5, and so on minutes before.
Okay, hello everyone. My name is Jelena. I'm a PhD student working on experimental searches for Lorentz invariance violation using very high energy gamma rays. Today I will tell you something about my work. First, I will tell you something about this framework in which I'm working, which Tomislav and Elisa covered yesterday very well. And then I will tell you something about the code that I'm working with my collaborators on, and then these two analysis methods that we are using. So without going in any underlying theories, when we want to constrain Lorentz invariance violation using very high energy gamma rays, we start from this modified photon dispersion relation, as we already saw that. So this E represents the energy of very high energy gamma rays. This EQGN is the energy scale at which quantum gravity effects should become significant. And then we have this parameter N. Now we are using only first two orders of this expansion. Why don't we go further? Because we are not sensitive enough to, well, detect them. Here we come to the first question. Yesterday, Tomislav asked, do we have any questions that we would like to have answered during this school or later? And I have three of them. First comes from this equation. Namely, we are using n equals 1, n equals 2. That's okay. 3, 4, 5, we cannot. Good. But this n can have also values 0 and -1. Okay, I can live with that. But it also can have values between 0 and 1. So it can have values of 0.7, for example. In that case, we are entering a world of fractal geometry. And this is something that I would like to know if someone is working on, because I would like to know, can I test it and how can I test it with my experiment? But this is, so if someone is doing that, please tell me. Okay, we have modified photon dispersion relation. We just presume we can take a derivative and we will obtain this energy dependent photon group velocity. Here, this parameter S can have two values, +1 and -1. And we see if it's +1, then our speed is greater than c, and we are talking about supraluminal behavior. Or if it's -1, then we are talking about subluminal behavior. Whatever the effects that modified photon dispersion relation may have, those effects are really, really teeny tiny. So, namely, even if we take these Pevatron sources that Elisa was talking about, this ratio is very, very small. So this is the downside. The good side is that those effects are cumulative. What I use later, you also saw this equation. So we have two photons of energy E2 and E1, and they are simultaneously emitted from our source. And if this modified dispersion relation is true, then they reach the observer at the different times because they have different energy dependent times of light. This time delay or time lag is proportional to this distance parameter. And one of the things that we are trying to do, well, we did in our code, is that first user can choose whether he would like to do LIV or BSR. And this is the first thing that will change. So these two frameworks have different distance parameter. Since I'm working with LIV primary, and this example will be done with this. So this distance parameter was derived by looking at the co-moving trajectories of particles, starting from their modified dispersion relation. Now, what sources do I need? And now I have a recipe, what I need, but in which sources should I look for that? Here up you can see like a very rough estimate what a source, what this EQG, this LIV limit depends on. So mainly it's proportional. We should see that both in linear and quadratic scenario, it depends on the maximum detected energy of our photon. The higher the energy, we are better. I will go here and say, okay, the further the distance, the better for us, but this brings some caveat. Namely, the most energetic photons, which would be affected mostly by the LIV, they would be absorbed in different background radiation fields. So we have a smaller probability of detecting higher energetic photons. And then we have this time variability. Namely, in previous slide, I told you the sentence started the sentence with two simultaneously emitted photons. This is quite strong assumption. And if our light curve is our flux is constant in time, every single photon has the same probability of being emitted in any of those times. But if our light curve changes with time, then we can constrain this emission time. Namely, we can do put better constraints. Three types of sources are good for those. First, first of those are active galactic nuclei. I will go on this side. Active galactic nuclei. Good side thing about them is that they are numerous. We have good statistics. The second are gamma ray bursts. Here, this divided in two sections. These lower energetic ones, we have a bunch of them, but those most energetic ones we have only 4 detected so far. And then we have pulsars, which are great. So time variabilities goes to milliseconds. Also, they repeat each other. So gamma ray burst, once it's gone, it's gone. But with a pulsar, it repeats its emission constantly. But the problem with them is this distance. So there are all of them in the Milky Way so far detected in very high energy gamma rays. So that's their caveat. So how do I use it? So I use this code called G-like. It's an open source. It's root-based code framework for the numerical maximization of joint likelihood functions. Mainly, it was used for gamma ray for dark matter searches, but it could be extended to some other topics. Here, what we have is this joint likelihood. This function has one free parameter that we want to constrain, and as many nuisance parameters as you wish, or as your statistics allow you. So what's the big deal about this? Let's see an example. So Now imagine that we have one of these pattern sources, LASSO J2032, and we have observed that source with Hess telescope. We can calculate our likelihood, and for now, that would be it. This is the all that we can do. What we are trying to do with this code is, okay, but I have this source observed also with MAGIC, and I can calculate likelihood with other telescope and with the third telescope. And then each of them has calculated its own likelihood. Then we combine those likelihoods in one single likelihood value. Then we have some other source, for example, Markarian, and then we also have observed it with, I don't know, Hess telescope and Veritas telescope. We also then combine those two likelihoods in likelihood of this source. In the end, what we can do, because LIV is, we presume it's not source dependent, we can combine those two likelihoods in one likelihood. What we get here is that every data set that we are now looking at separate data sets can contribute to our calculation. I bet you like this equation. So we are using two methods, unbinned maximum likelihood analysis and binned. Here is written a likelihood function for the unbinned maximum likelihood. First, tell me something I will tell you something about the observations. How do we observe the MAGIC so that these letters have sense? So when we are observing with imaging atmospheric Cherenkov telescopes, we have some region in the sky around the source, and this is our own region. It's some circular region around radius around 0.1 to 0.2 degrees. In that region, we count our events. That region contains both signal and the background. Then we need to somehow to estimate our background. So we move to another region where we presume there are no sources, and then we count background events from that region. This off region is of the same size and shape as our own region. Off regions, we can choose more than one, 2, 3, 4, 5. And this is why we have this normalization parameter. So this would be a probability that our signal event belongs to a signal or to a background. Okay, we have this probability distribution function for our signal and for our background. And here we put everything that we know about our observation. So here in the end, we have collection area, energy resolution, bias, everything that we know about the telescope. This here is observed spectral distribution of gamma rays. Namely, we heard that modified photon dispersion relation can modify also the spectra. But here, when doing this analysis, we are presuming Lorentz invariance scenario. So here we are not putting inside LIV scenario, and here comes my other question. I don't have time for it. And the one last thing that we have is this observed light curve, and written like this, we somehow correct it for a potential time delay caused by the LIV. This means that we in the end get some light curve, which is called intrinsic light curve at the source, and it's called often light curve template. So let's see an example how it works. We have two data sets. These two data sets could be, for example, BLAC, one AGN source observed with MAGIC telescope, and one with LST, two telescopes close enough one to another. Under our energy distribution has a spectral index of -2. Then our data, of course, has some time distribution. And I used here that the time distribution for both of them is Gaussian. It's okay assumption because it's the same source. And the telescopes are pretty close to one another. But also in my signal, we know that we have our background, and background has 0 temporal construction, so it's just flat. And we took some 18 minutes, which is standard time of observation. What we get, what I now have my data, what I need to do is to build my template. Now in this, I include everything that I know. So here we build it for a signal and for the background. Here for the signal, our energy distribution is, again, power law. Our time distribution is Gaussian. To be a PDF, we need to normalize it and combine it. And this plot contains every single information also about my telescope, of my instrument. Now, when I have both of these, I run likelihood program, and what you get is, okay, for my first data set, for example, my Markarian source from Hess telescope, I get eta, some value of eta parameter, which is parameter that I was looking for. Again, I do the same for the others, for the same source with other telescope. And then those two are combined in this joint likelihood method. Here you can choose some statistical parameters. So whether you like 95% confidence level, one-sided, two-sided, or other stuff. So we see, okay, it's converging, it's working, but let's see what happens if I induce some real-time delay. So here I have one data set. This is blue. And then into that data set, I introduce some time delay artificially. So I put this eta to some value. And here you can see how from this eta parameter, we can get this quantum gravity limit constraint, because this distance parameter is easily calculable. And what I get is this. First, this is the reasons why we need statistics. I was lazy here and used pretty low number of bins, so meaning that my template was really, really rough. But here, I needed to increase my binning, and when I increased that binning, my likelihood profile looked way better. Problem was that I didn't get the value that I had, that I have inserted. Now I know that what I inserted, and that means we investigated it and we have some bias. So just our pure analysis without any data, and we know everything in this example, has some bias. So we needed to correct for that. The other method that we are using is the bin maximum likelihood method. So we have Poissonian of our on events and our off events, signal and our background. And what's the big difference of here is that the template for the off region is not needed anymore. Namely, I could just take it from my off region, because my data as I get it is binned already. In that way, I have all information about my telescope energy resolution and bias already in the data. So it gives some better handling of systematics, and we are currently implementing that method. So to conclude, G-like is numerical maximization method for joint likelihood functions. You can use it and modify it for whatever you are doing. What our aim is to combine data from different telescopes or same telescopes, but with different telescope performances. We are doing that with two methods. One is unbinned maximum likelihood analysis, which relies on, let's say, known PDF, but in reality, that known PDF is not so known. Binned maximum likelihood analysis, on the other hand, does not require template for our off region. This should slightly decrease sensitivity, but it would provide more robust results. And stay tuned for the next results.
Thank you very much.
Welcome.
Very, very interesting. So, any question?
dimensional bunch of the different telescopes?
What?
The first time that it has been found to compute
Yes and no. Well, this idea comes from the DCLIV consortium that Tomislav was speaking about. So they are trying to do that, but with completely different methods. So by now, there is no published result on combined analysis from on time of flight studies with different telescopes. So yes, what this would do would make this analysis quite easier. So you as a user could input just your files that you would like to analyze and provide with source redshift and also with some description of your template. So you could choose from different parameters. And in theory, you just click after 24 plus hours, you get your limit.
Okay. I have questions, but maybe I will ask you later because we want to go on with the talks. So we thank Jelena again. And our next speaker is Giuseppe Fabiano, who is going to go more on the theory side and tell us about spectral dimension.
Can you hear me? Okay. The pointer. Okay, so as also Renate Lol was recalling the other day, many theories, many quantum gravity theory proposals predict that at some particular scale, which should be around the Planck scale, space-time should exhibit a fuzzy behavior, or namely quantum behavior. So if in this particular regime, we are losing those smooth properties that we have of Riemannian manifolds, we have to rethink our definition of dimensionality. So the definition of Hausdorff dimension should not be viable anymore, and we should require a new concept of dimensionality. One of the proposals for this concept is the so-called spectral dimension. So the starting point here is to consider a Riemannian manifold M equipped with the metric H and consider a fictitious diffusion process on this manifold. The reason why we are considering a fictitious diffusion process is because many physical properties of diffusion heavily depend on the dimension of the manifold we are considering. So this should be a good indicator of effective dimensionality. So we start with the diffusion equation, which is DDS minus the Laplacian of the diffusion function rho that depends on the starting point x, the end point of the diffusion x prime, and s, which is called fictitious time because it's not a variable that we are using to describe the manifold, and it does not even have the dimensions of time if one does dimensional analysis on this equation. So the Laplacian is the usual one that is considered on Riemannian manifolds equipped with a metric that is non-flat. And plus we require that the diffusion function satisfies the initial conditions, namely that when s is equal to 0, our diffusion function is proportional to the delta function of x minus x prime. So now what we can do, we can try to solve this equation and calculate a quantity that is called the heat trace that is shown in the lower part of the slide. And one can show that this quantity is actually also equal to what is called the return probability. The return probability in a diffusion process is basically the probability that the walker that is doing the diffusion on the manifold starts from a point x and returns to point x in a fictitious time equal to s, basically. So when one is equipped with the definition of return probability, one can go and calculate what is called the spectral dimension, defined as -2 times the log derivative of the return probability with respect to s. So now that we are equipped with this definition, let us try to apply it in some case that we already know and see then how it behaves in other case. So the first case that we might want to consider to check the validity of the definition is the flat Euclidean case, in which the Laplacian is just the dA sum over A subintendent. And in this case, we can easily solve the diffusion equation in Fourier space, gaining the expression of the return probability that will be proportional to S to the power of -n/2, where n is the number of topological dimensions that our Euclidean flat manifold has. And so by a simple calculation, one obtains that the spectral dimension of the flat Euclidean case is just equal to n for every value of s. Basically, we have no what is called dimensional rounding. But now, since we have said that the new definition of dimensionality has something to do with quantum gravity, and in quantum gravity we are mainly interested in considering Lorentzian manifold, how can we treat them in this purely Euclidean setting? So the main idea is, let's start trying to repeat the calculation in flat Minkowski spacetime in n+1 dimensions. So we have the generalized Laplacian, also called the D'Alembertian. If we try to repeat the same calculation for the diffusion equation that we had done before, we obtain a divergent result for the diffusion function rho. So the main trick here, the main technique that is employed is to actually use a Wick rotation, so sending time in imaginary unit times the time. And so we get an expression for the return probability that now we are familiar with because we just saw it in this other slide. I just represented it here because I wanted to highlight the argument of the exponential here. So we have k squared and omega squared. I have separated the variables just to show you that what is mainly important in calculating this spectral dimension is the Euclid version of the dispersion relation. So what I have in the exponent is just the Fourier transform of the Laplacian with the Wick rotation employed. So I'm actually writing here the Euclid version of the dispersion relation. And so since here it's like calculating the Euclid spectral dimension in n+1 topological dimensions, again, I get the constant value of n+1. But now, since we have discovered that the dispersion relation plays a crucial role in calculating the spectral dimension, what happens if we modify them in the spirit of what we have heard in these past few days? So one example I wanted to show in this regard is and it's an example that connects non-commutative spaces and modified dispersion relations. So fuzzy spaces and modified dispersion relations. It's the case of the kappa Minkowski non-commutative space-time that is defined by the brackets shown in the top of the slide. And what one studies, and I will not talk about it here because of time, is that there exists an algebra called the kappa Poincare algebra that leaves that commutator covariant. And this algebra has a Casimir that, in the spirit of the physics that we do, we interpret in a semi-classical way as a dispersion relation. And so in this case, gaining semi-classical inspiration from the Casimir element of the kappa Poincare algebra, we obtain the modified dispersion relation that is shown in the slide in the case where the mass is equal to 0, basically. And studies of the spectral dimension have shown that if one considers a modified dispersion relation of with increasing powers of k, so alpha 1 and alpha n are increasing exponents, one obtains the asymptotic behaviors that are shown at the bottom of the slide. So for these asymptotic behaviors, I wanted to discuss with you what is the meaning of the evolution parameter s going to 0 and the evolution parameter s going to infinity. So we can interpret s going to 0 as probing the ultraviolet regime, since this means it is equivalent to saying that the Walker that we are probing space-time with has an infinite energy. So we are probing the ultraviolet regime, while when we send S to infinity, it's like we are probing our manifold with a Walker that has energy much lower than the ultraviolet scales that we imagine should be in quantum gravity. And so we call it the infrared regime. And in this case, we observe that in the infrared regime, we obtain the value of 4 in case if n is equal to 3, so the actual classical Minkowski that we are used to study physics with. And however, in the ultraviolet regime, we get the dimensional reduction and we get the value of 3. So we get a different number of effective dimensionality due to the deformed dispersion relation. So dispersion relations are telling something to us something about the effective dimensionality at the ultraviolet scale. So now I wanted to depart from flat cases and actually start to studying curved spaces and topologically non-trivial spaces. The one I wanted to talk about here is both compact and curved, and it's the case of the two-sphere, which is defined as the ratio of defined as the quotient of the SU2 group over the U1 group. So here in the slide, I've just written down the formula for the calculation of the return probability, so the heat kernel for homogeneous spaces, which can be written as the quotient between a group and the isotropy group. And the formula here in the last part of the slide actually shows that this formula is proportional, is intended as a sum over all representations of the character of the representation Kj. Dj is the dimension of the representation, and we have the exponential of -s times the Casimir of representation J. So these are just formulas that allow us to calculate the heat kernel in this particular situation. In the case of the sphere, we have that the Casimir is L times L plus 1, and when we plug this in the previous formula, we obtain a simplified expression for the return probability on the two-sphere. And this, when we try to also here evaluate the spectral dimensions at the asymptotic regimes in the ultraviolet, we get the number 2, which is correct, because in the ultraviolet regime, as we do when actually defining Riemannian manifolds, we are looking at the manifold up close. So it's the role of curvature is not present. We do not see the curvature. It's like we see basically a plane. But when we would probe the sphere at infrared values, we get a spectral dimension equal to 0. And this is, you can kind of imagine this as looking the sphere from far away because you're probing it with an infrared Walker. So it's like you see no dimension at all. So now, in the spirit of also talking about quantum spaces, what one can do is actually consider a quantized example of the sphere called the quantum sphere. In this case, the SU2 group is replaced by the group called SUQ2, where Q is a deformation parameter. And the algebra function of SUQ2 is defined by these generators, which satisfy commutation relations that are deformed with respect to the basic SU2 case. And here the deformation parameter for convenience is called Z equal to the logarithm of Q. We all of course, recover the case of the sphere when Z goes to 0 or Q goes to 1. And here, so in order to complete this deformation of the sphere, we also have to consider a deformed Casimir element in representation J, which is just one way I've shown here. And by repeating the calculation techniques that we have already used in the case for the sphere, we obtain the following result. In this graph with label A, I've just shown the spectral dimension running for the classical sphere, which we have said in the UV is equal to 2, and then in the IR starts going to 0. For the quantum sphere, we actually exhibit peculiar behavior. So in the UV, we actually have that the dimension approaches 0. Then it goes up, quite not reaching 2, and then decreases again when we go to the IR regime. So that is just to show how basically quantum features can alter our notion of dimensionality if we take into account this new concept of spectral dimension. So now that we have reviewed the sphere and the quantum sphere, what we wanted to do was to try to disentangle the role of the compactness and of curvature when considering these manifolds and see how these characteristics of the manifolds play their role in the running of the dimension. So first, I will present the cylinder, which is a flat 3+1 cylinder, which is a flat 4-dimensional space with a compactified dimension, which means that one of the coordinates is equivalent to the coordinate itself plus 2 pi r, where r is the radius of compactness. When I try to solve the diffusion equation on this cylinder, basically, I get that the Laplacian is undeformed because I'm still considering a flat manifold. But given the periodicity of the coordinate xi, I have to enforce a periodicity on the solutions. And what this does basically is that when passing to Fourier space, and so considering basically the conjugate momenta to this coordinate xi, one of the integration becomes basically a summation that appears then here in the final result of the spectral dimension. And when we actually evaluate this numerically, we see the following behavior shown here in the graph. So in the UV regime, we are looking at this cylinder up close. So basically we are seeing a dimension of 4, as we would expect. But then when we go to the infrared, so we probe the cylinder with infrared, with an infrared worker, we get a dimensional reduction again to 3. So in this case, we have seen that compactness actually shrinks the dimensions when we go to the infrared regime. So now let us turn to a pure curved case, which shows to be the hyperbolic plane, h of n+1. And this is basically defined as the set of all t and x vector with t greater than 0 with this particular metric. And again, here, as we said in the initial slides, the Laplacian is quite different because we are considering a curved case. And here I wanted just to show you in the case of n equals to 1, so with the hyperbolic planes, which are the geodesics of this particular Riemannian manifold. And the reason is because that when we try to solve the equation for the diffusion, when we try to solve the diffusion equation for the hyperbolic plane, we get some solution that depend basically on n and also on the geodesic distance that here I have indicated with rho. So rho is the geodesic distance between the endpoints. And what we can do here also, in the spirit of what we were doing before, so trying to evaluate the spectral dimension for ultraviolet and infrared regimes, we actually see that when S is going to 0, so in the ultraviolet, for any n, we get this particular asymptotic behavior, and in the infrared regime, for every n, we get this other asymptotic behavior. And then, using the definition of the spectral dimension, seeing the Poincare hyperbolic plane up close, we recover the expected dimension of n+1, but when we go to the infrared regime, we get a dimensionality that is equal to infinity. So basically, what I just wanted to show here is that we wanted to try to understand better the definition of spectral dimension by disentangling the role of curvature and compactness. As we have seen, compactness is responsible for dimensional reduction, while the role of curvature actually is still not clear, because I have shown you an example with negative curvature in which the effective dimensionality goes to infinity, but the classification still needs to be completed, for example, with the non-compact space with positive curvature. That would complete actually the classification. So thank you for your attention.
Thank you very much.
Questions?
I have a question from a student.
Very nice.
This is more likely a question about zoology than about physics. So you talked about negative curvature and the possibility to expand to positive curvature. Do you expect that maybe there could be methods developed for manifold with curvature which varies in different points? Like if I want to study the effective dimension in a localized region with positive curvature, and then I go to negative curvature, do you think?
Yes, so basically what is actually already written in the literature is that when you have a curvature that depends on the space point of the manifold, you define the effective dimensionality actually as the mean of what you would calculate locally over the whole manifold, basically. So it's an averaging of the dimension in every point of the manifold. That would be what you would do.
Is there any other question? Someone proving another point? Okay, if not, we thank Giuseppe again.
Thank you.
We go to our next speaker, who is Sjors Heefer, and he's going to tell us about Randers PP waves. Thank you. You can put this on.
I warn you, 10 minutes.
Yep. All right. Thanks. All right. Well, first of all, I would like to thank all the organizers and also the lecturers. I've been really enjoying this course so far. And I'm also glad that I have the opportunity to present some of my own work. As you might see, I changed my title a bit. So my original title was Randers PP waves. And to give you an idea, this is one of the solutions. This is a vector solution to the field equations in Finsler gravity that we recently discovered. This is work with Christian Pfeffer and Andrea Fuster. And so I would really love to tell you everything about these Randers PP waves. But I only have 15 minutes here, and so I decided that it would probably be a better idea just to try to give you a global overview of Finsler gravity. And then in the end, depending on how much time I have left, I may also say something about these Randers PP waves. So Finsler gravity, you might describe it as the study of Finsler space-time geometry. And so the idea is that we try to build a theory or a framework which is as close as possible to general relativity, but has a more general underlying geometric structure. So instead of pseudo-Riemannian geometry, we now want to generalize this to what we call Finsler geometry. And then we want to build a theory much like GR, as much as possible, but with this more general geometry. And you might ask, why would we even want to consider such a theory, right? And there are various reasons, but for me, the most important one is comes from quantum gravity phenomenology. If you consider modified dispersion relations, Lorentz invariance violations, or deformations of deformations of Poincare symmetries, then it seems that all of these models have in common that you need some kind of more general geometry than pseudo-Riemannian geometry to describe these models. And so that to me is a clear sign that we should at least try to understand theories like this, where what we're doing is exactly generalizing the geometry. Now, of course, we want to describe the interaction between the space-time geometry and the matter content in the universe. So we also need a field equation, and this field equation should then extend the field equation in general relativity. And these are the main two things that I want to discuss today. So first of all, I'll try to give you a general introduction to what we mean by Finsler geometry, and then also try to explain why this actually is a good model for space-time. And then we'll see the field equation, in particular Pfeiffer and Wolfhardt's field equation, which extends Einstein's field equation. And then if I have some time left, I'll talk about my own research in which we considered a very particular type of geometries, Barrel-Randers geometries. We could completely classify then all solutions to these field equations of that type, and those are these Randers PP waves. Okay, so the main way in which Finsler geometry generalizes Riemannian geometry or pseudo-Riemannian geometry is that the usual geometric objects that you all know from Riemannian geometry become now dependent not only on the position in your manifold, but also on the direction. And so we describe this as follows. If we have coordinates x on our base manifold, which will usually be space-time, then this induces coordinates on the tangent bundle, which we can denote by x, y. And so we have now x denoting the base point and y denoting a vector at the point x. And so most of our geometric objects will generally become functions of both x and y. And the first example of this is the Riemannian metric, or rather the generalization of the Riemannian metric, often called the fundamental tensor in Finsler geometry. So this will now become dependent on the position and the direction in your manifold. What I also want to say is you can also think about this whole framework as defined on the cotangent bundle rather than on the tangent bundle. It's just a different formulation, but then this is perhaps more interesting from the quantum gravity phenomenology point of view, because then you get, instead of tangent vectors, you get momenta, canonical momenta, and you might
think of this metric here as a space-time metric that depends on the momentum. So that, of course, would be very interesting from that point of view. Now, usually we consider this fundamental tensor as a derived object, and the fundamental object in Finsler geometry is actually the infinitesimal line element, which we say, okay, let's write the infinitesimal line element as a generic function on a tangent bundle. We call this the Finsler function, and then we ask the question, what are the conditions, the minimal conditions that this function should satisfy in order that this leads to a well-defined geometry, well-defined geometric structure, and a natural length measure. And this is what the definition of a Finsler space tries to answer. So a Finsler space is a smooth manifold endowed with a Finsler function, which represent the infinitesimal line element, that satisfies these three axioms. And I want to go through each one of them. So the first one, homogeneity, says that if you have a vector and you scale it with a certain positive number, the length of that vector should scale in exactly the same way. And what this translates to is that the length of curves is actually independent of the parameterization of the curve. And that's, well, from a geometric point of view, that's already a very desirable property to have. But from a physics point of view, it's essential, I would say, because this is what allows us to define the proper time of an observer as the length of a world line. So this, this is a very good property, and I find it difficult to imagine a theory like this, which is even more general than this, because it becomes very hard to define what you mean by proper time. Okay, then we want f to be smooth, usually. And thirdly, we now define the fundamental tensor, and in this way, as the second partial derivative of the squared Finsler function. And this will be the generalization of the Riemannian metric. So we want this thing to be positive definite. And the good thing is, if we do this, then we can actually reconstruct f from this fundamental tensor in the same way that we would usually do in Riemannian geometry, except that now this Gij depends on the direction as well. An example of a Finsler function is given by the Randers metric, which is conceptually very simple. You just start with a Riemannian line element and you add linear deviation. So Aij is some Riemannian metric. We construct its infinitesimal line element, and beta is some one form. We construct the Randers metric by taking this Riemannian part and adding some linear deviation. Now, of course, we want to describe space-time, and so we want to change one thing, which is the signature. And here there are actually some technical details which I'll skip over. So for our purposes, we'll just say that a Finsler space-time is defined by this definition, but with Lorentzian signature instead of positive definite signature. And then also for the Randers metric, we would usually start from a Lorentzian part and add a linear deviation to that. All right, then let's have a look at the field equations. So this is the vacuum field equation by Pfeiffer and Wolfhard. And this is an extension of Einstein's field equation in the sense that if we now take a Lorentzian metric, so by that I mean a non-Finslerian Lorentzian metric, and we put it in here, then this equation just reduces to Einstein's field equations. Now, you might say, okay, that's all very well, but how do we know that this is, in fact, the right equation also for properly Finslerian spaces? And so the way in which this equation was derived is by starting from the Poincare, the Einstein-Hilbert action, sorry. And you can generalize this in a very natural way to Finsler spacetimes. And then you compute the variation and you set it to 0. And this is exactly the equation that you get out. Now, it was recently shown that you can also arrive at this equation in a different way, namely starting from the geodesic deviation equation. And then in exactly the same way as you can use that starting point to arrive at Einstein's field equations. If you follow the exact same steps, in the Finsler case, then you also arrive at this equation. So although there are several different proposals in the literature, say that this one is definitely the most natural one, also has the most robust foundation. It is, however, very, very complicated. So what one would like to do is try to find ways to simplify this equation if you want to be able to solve it. And so this is one of the things that that we did in our research. So we considered a particular type of Finsler geometry. I'll spare you the details, but it's called they're called Barwald-Randers spacetimes. And we proved that for those kinds of geometries, this field equation is in fact equivalent to this one, just the vanishing of the Ricci tensor. And that's, of course, a very good result, because this is just the formal equivalent of Einstein's field equations. And we know a lot about solutions to Einstein's field equations. So this actually allowed us to classify the solutions of this type to the field equation in vacuum. And then I'll skip to my last slide. So this is this was our final result. So we proved that any four-dimensional non-trivial Barwald-Randers solution to the vacuum equation in Finsler gravity must be of this form. So it's a Randers metric by definition, and then the Lorentzian part had to be a Lorentzian PP wave metric. So this is an exact gravitational wave solution to Einstein's field equations. And the one form, beta, must be the defining covariantly constant null one form corresponding to this PP wave metric. And then we put a factor lambda in front, because we probably want to consider solutions that are close to the Lorentzian solution. So this lambda would be a small constant. And if we put all that in explicitly, then this becomes the final expression for our Finslerian line element. Now, the obvious question, of course, becomes how should we interpret something like this? And in particular, are there any phenomenological consequences of this, and are there observational differences between this Finslerian geometry and the corresponding, let's say, unperturbed Lorentzian geometry? And this is, yeah, I think this is a very important question, and this is what I'm currently trying to understand. But in general, this is very difficult to do in Finsler geometry, to extract a phenomenological consequence, which is not just a coordinate artifact, which of course in GR is already an issue. And here this becomes even more difficult. So yeah, so that's what I'm currently investigating, and that's where I'll stop. Thank you very much.
Thank you, Sjors. Any question? Okay, 1 and 2.
When you write down the field equations, I think it was slide 6 or something. What was the S?
Yeah, so I skipped over defining all these objects because it would take some time. So S is called the mean Landsberg tensor, but what it essentially measures is the nonlinearity of the connection. So usually on a Lorentzian manifold, you have the Leibniz-Vida connection, which is the unique torsion-free metric-compatible linear connection. And so in Finsler geometry, you can kind of do this same construction, but you will usually not get a linear connection. And this S, in a sense, measures the nonlinearity of the connection. So for Barwald spaces, which I can now define them, Barwald spaces are ones that have a linear connection. This whole part vanishes identically.
And is it obvious that, or like, can you see from that you kind of this reduces to Einstein's equation, or is that a longer cut?
Yeah, I think you should write it down. You can do it in a few lines. To be honest, I would have to think about it, how to do it exactly again, but you can do it in a few lines. You take a few derivatives. The point is that, so this whole term vanishes for Lorentzian manifolds, and this mu nu, which in Finsler geometry is generally direction dependent, now becomes just a function on the manifold. And so by differentiating a few times, you can get rid of these y mu's, and you're left essentially with the R mu. That's the idea.
Yeah. My first two questions were exactly the same.
Okay.
No, but like it might be a nice question, but for example, if I just take the standard general relativity, we know that on a tangent plane, it has to boil down to the special relativity. So on the Fenslerian, if you're trying to modify the general relativity, that will cause changes in special relativity and accordingly the classical mechanics of it. So yeah. Hamilton-Jacobi equation. So is it not possible to extract phenomenological implications from the special relativistic changes of the Fenslerian geometry?
Yes, so that would definitely be the first step, I would say, to try to figure out what the phenomenological consequences are. But still then it's very difficult because it's difficult to describe observers and in particular how they measure distances, for instance, because you don't have a unique orthogonal like spatial hypersurface given an observer world line. It's more difficult to construct that than in general relativity. And so most you can say, at least as far as I'm aware of, most you can say is local phenomenology at the point of the observer. But of course you would like to be able to extend that to real physical
the space-time will continue to be a globally hyperbolic space-time, even if you are modeling using a Fensler geometry.
Sorry?
So the space-time will continue to be a globally hyperbolic space-time, or no?
Globally hyperbolic, what do you mean exactly by that?
Like if I go to say Hamiltonian variation, the ADM formalism, using this particular thing, the concept of time can still be chosen in terms of like there's a time and then there are three-dimensional hypersurfaces.
Yeah, you can do that. Yeah, but that's probably a bigger assumption than it would be in general relativity, because these time and space splits, you have more ways to intertwine them. So to say that you necessarily have time axis times spatial slices would probably be a bigger assumption. But if you assume that, then I guess you can still repeat that formulation. I don't think it has been done, this formulation. It would be interesting to repeat that, but conceptually you can definitely do it.
Thank you.
Okay, I would say that we thank Sjors again.
Thank you.
And we have, last but not least, our final speaker. So we have Silvia Pietroni, who is going to tell us about gravitational lensing in wormholes.
There's a pointer and then button. Okay. Good evening, I'm Silvia Pietroni. I'm going to talk about gravitational lensing by wormholes in binary systems. I will make a brief historical introduction about light deflection. We know that space-time is curved by the presence of massive bodies, and this curvature influences the motion of the bodies. Can you hear me? Okay. So I was saying that space-time is curved by the presence of massive bodies, and this curvature influences the motion of the body themselves. So one of the consequences of that is that even the light that is supposed to be massless bends its trajectory while passing close to a massive body. This was already theorized by Einstein in 1913, and then was demonstrated by Eddington, a British astronomer, during the solar eclipse of 1999 in Principe Island. During this solar eclipse, he measured the position of the stars, and he just showed that they were moved by an amount precisely predicted by Einstein some years before. What I study is gravitational lensing by object whose gravitational potential asymptotically falls as 1 over r to the n. This kind of potential gives rise to a deflection angle that goes as 1 over theta to the n. So this is, sorry. Okay, this is the configuration of a system. So S is the source position, L is the lens, O is the observer. So when the ray of light that starts from the source passes close to the lens, we have the light deflection. So the real position of the source is under an angle called beta, and the image that we observe is under an angle theta. So the deflection angle goes as 1 over theta to the n. This kind of potential are really important in this context. For example, we can describe through this kind of systems galaxies with halos described by different power laws, or also system composed by 2 black holes, 2 neutron stars, or a system composed by wormholes or exotic matter. What I'm going to introduce is only an application of this kind of systems, and is lensing by wormholes. But as I told before, we have many configurations of this. We know that Alice wormhole has 0 mass, special infinity, but it causes light deflection. This kind of objects were studied by many authors, and recently they were investigated as an observational probe of exotic space-time. One of the effects seen as a distinctive signature of this exotic object is the demagnification effect. This effect is not present in lensing from ordinary matter, but it's only present in this kind of lensing with this kind of objects. So this kind of metrics were investigated first by Kitamura in 2013. And we can see through this formula the demagnification of the total lensed images. That is this one. And this is evidence of Alice wormhole and might be used for hunting the source of exotic matter in the case of n greater than 1. I want to remind the meaning of the exponent of this kind of potential, that is n. N is the ratio between the tangential and the radial pressure. And according to the value of n, we can have different kind of systems. N between 0 and 1 may describe galactic halos. In particular, n equal to 0 is the isothermal, is a single isothermal sphere. N equal to 0.5 is a galactic halo, n equal to 1 is an object described by Schwarzschild metric. For n equal to 2, we have the Alice wormhole, and for n greater than 2, we have exotic matter. This is the lens equation. Through the lens equation, we can find images. We remind that beta is the source position, theta is the position at which we observe the lensed image, and we introduce another parameter that is gamma, that is called the strength ratio, that is simply the ratio between the 2 Einstein radius of the 2 lenses, that in this configuration we simply call A and B. And this is another image of the system. We have the source, and then we have the shifted images after the lensing. Now I'm going to introduce the critical curves and caustics. We know that the number of the images formed at a given source depends on the source position. This region with a different number of images are delimited by caustics. So we take the lens equation and we put the condition j equal to 0, where j is the Jacobian determinant of the lens map. Through this condition, we find the critical curves. The critical curves are on the lens plane. starting from the critical curves, we apply the lens map on these critical points, and we find the corresponding caustics on the source plane. Why are these caustics so important? They are important because when a source crosses a caustics, there is a new pair of images. What I investigated are 3 cases according to the parameter gamma. So for gamma equal to 1 is the equal strength binary. For gamma equal to the square of 0.1 is an equal strength binary. It means that the bigger lens is the standard one with a fixed n equal to 1. So in my system, I put one lens fixed with the index n equal to 1, and then I change the second lens in order to see what happened to the system with respect to the standard case. And the third case is the reverse unequal strength binary with the standard lens that is the smaller one. In this presentation, I will show only the first case. Then I will show 3 separation because we start from a wide separation and then I move these 2 lenses closer. So we have the wide separation, the intermediate separation, and the close separation. The separation is the distance between the 2 lenses. We start with this example. These are above the critical curves of the standard binary lenses. What does it mean? It means that we have 2 lenses, 2 standard lenses with n equal to 1. So the potential is 1 over r. And by standard, I mean a Schwarzschild object. Symmetric because both lenses have the same index for the potential, that is 1. So the first one is in the close separation, then the intermediate separation, and then the wide separation. Above, we have the corresponding caustics that we find by applying the lens map. So the red case that we will see even in the following plots is the standard case that we take as a reference. Botts and Melchior in 2016 already investigated the symmetric case for this kind of potential. By symmetric case, I mean that the 2 lenses have the same index, not only 1. So n equal to 1, m equal to 1, oppure n equal to 2, m equal to 2, and so on. So 2 black holes, 2 neutron stars, 2 wormholes, so a perfect symmetric system. This is one example of caustics for exotic matter, so in the case for n greater than 2. And this is an example in the close separation, and we can see the existence of giant caustics that are the blue ones in this case, in this example. These are my results. I extended this symmetric study to a generic one. I keep fixed the index for the first lens, n equal to 1. So the first lens is a standard object, a Schwarzschild object, and I vary the index for the potential of the second lens. We can see what happens. So I remind that I call for the first lens the index n, and for the second lens the index m. M equal to 0 is the isothermal singular sphere, m equal to 0.5 is a galactic halo, m equal to 1 is a Schwarzschild object, a black hole, a normal star, m equal to 2 is a wormhole, and m equal to 3 may describe exotic matter. So we can see that for smaller values of the index m, we have a deformation of the critical curve. While for greater values of m, these critical curves are not deformated. This is why they feel a weaker tidal field from the second lens. For the corresponding caustics, we have this kind of behavior. For greater m, the caustics become smaller and they move toward the left direction. This is for the wide separation. So let's see what happens if we put these 2 lenses closer in the intermediate separation. So we can see that the critical curves now are united. They are bigger for smaller values of the index of the potential, while the caustics has the opposite behavior. So they are bigger for greater value of M, of the index M. We remind that the standard case is the red one, and the yellow one is the one with the wormhole, and the green is for exotic matter. Then we put these two lenses closer in the close separation. We see for the critical curves on the left panel the appearance of primary critical curves. They are the smaller curves inside the bigger curves. So there is also this kind of behavior. We have this primary critical curve that moves toward the first lens with increasing M. And in the case for M equal to 0, that is the isothermal sphere, we have a degeneracy over the second lens. So the two critical curves are attached. And this corresponds to two open caustics that lies along a dashed circle that is called the pseudocaustic. And this is a strange behavior that appears only for the value of M equal to 0 and only in the close separation. So this is only an example because the complete atlas of the plots is on the paper. Another strange behavior that we can have only in the close separation and only in the range between 0 and 1 is the elliptic umbilic catastrophe. That is this strange behavior of the critical curves. They shrinks to 0 for this value of separation equal to 0.774. Then this is a plot of the transition between the topologies. So the upper curves are the transition from the intermediate to wide transition. And these are found analytically, while the transition from close to intermediate separation, are the curve below, are found only numerically. Another application of the caustic evolution is a limit called planetary limit. That is the limit in which one of the two lenses is much smaller than the other in the case of two Schwarzschild objects, so with the index equal to 1. In this case, in this planetary limit, the caustic of the perturbing object has an extension in the parallel and in the y direction. So with respect to the caustic that I showed you before, we can see the extension in the vertical and in the parallel direction. So my conclusion are that these mixed binary systems are important for several reasons. First of all, we can use this kind of models in the investigation of pair of galaxies with different halos. So we are in the range in which the index of the potential is lesser than 1. This system can be used in the opening of a new channel in the search for wormholes when they appear in non-isolated environment, because in this case, we know we have a normal object and then a wormhole. So this is the distinctive signature. And we can use also in the case in which one object is made up of exotic matter and the other one is a normal star. And thank you.
Thank you very much. Questions? I go with the first one. So, is there a specific reason why you were studying binaries specifically? Why were you not studying one single lens on its own?
No, there is no particular reason. We started with a binary system and now I'm studying another kind of system. It's always binary, but there is no particular reason.
Yeah, I guess when you are going to say the limit when one is much stronger than the other, that would... So here they have equal strength, no? If you want to study a case where one...
this is the equal strength, yes. But this is also... in the paper, this is the complete atlas with the reverse unequal, the unequal, but it's so.
Yeah, I guess if you say the limit where one is much weaker, then it is basically as having only one object. No?
Yeah, it depends on the potential. Yes.
Yeah. Other questions?
I have a question which, I mean, I don't know if I understood correctly, but these two lensing over there, for example, these 2 points, so the lines that we see around them.
I can hear.
Sorry, oops. Can you hear me now?
Yes. No.
So in these 2 points, the lines that we see around them are what exactly? Because are the images of...
No, they're not the image. No, it's quite complicated because, so as I told you before, we start from the lens equation that describes the lens configuration of the system, so the 2 lenses in this case. On this lens equation, we have to compute the Jacobian determinant of the lens map. The condition j equal to 0 define these critical curves. These critical curves are on the lens plane, okay? And starting from the critical curves, we find then on the source plane the caustics. The caustics are this one below, or in this case on the right. Okay, the caustics are important because when a source crosses a caustics, there is a creation of a couple of images, okay, of the source we are observing. So,
okay.
This is the importance of.
Sorry.
Question? I think we can thank and thank you to all the speakers of this session, and have a nice evening and see you tomorrow.